I'll proceed now to introduce Mark Musin and Karen Verspor as we begin our excursion into the world of large language models and discrete knowledge objects. So Dr. Musin is professor of biomedical informatics at Stanford University, where he's director of the Stanford Center for Biomedical Informatics Research. He conducts research related to open science, data stewardship, intelligence systems, and biomedical decision support. He's principal investigator of the National Center for Biomedical Ontology, one of the original national centers for biomedical computing created by the U.S. National Institutes of Health. He's also the co-editor-in-chief of the journal Applied Ontology. Professor Karen Verspor is Dean of the School of Computing Technologies at RMIT University in Melbourne, Australia. Karen's research primarily focuses on the use of artificial intelligence methods to enable biological discovery and clinical decision support through extraction of information from clinical texts and the biomedical literature and machine learning-based modeling. She is also the Victorian Node lead and co-founder of the Australian Alliance for Artificial Intelligence in Health. So we greatly appreciate Mark and Karen and the presentation that they are about to give.
Thanks, Chuck. As you know, you've asked Karen and me to get together and talk about the whole issue of large language models and where they stand with respect to the MCBK initiative. I guess when you look around and you see almost every human activity right now, there's concern that natural language processing somehow is going to put an end to life as we know it on the planet in terms of all human endeavors. I don't think that's the case. It's certainly not the case with MCBK. And Karen, as an expert in natural language processing, certainly has strong opinions on this topic, as I do. Karen, is the world safe?
Yeah, the world is definitely safe. No intelligence actually lurking in that machine.
I think it's helpful, actually, when we think about what the role of natural language processing is, and LLMs in particular might be. It's helpful just to think about what MCBK is all about. For a lot of people, it's just a bunch of letters, rather, that sort of gloss off the tongue. We think about whether something is mobile, whether it's computable, whether it's biomedical, whether it's knowledge. And from my perspective, I think we can view LLMs in each of those dimensions and sort of decide whether they actually fit the MCBK parameters or not. What is your sense, Karen, about mobility?
Yeah, mobility is an interesting one, right? Because if we're talking about large language models or other foundation models, these things are massive, and they, have terabytes of parameters and space in data centers that they need. So they're really not mobile in any kind of meaningful way. Now, of course, we know that we can bring data to these models, and we don't necessarily have to move the models around themselves. So that changes the notion of mobility. Certainly, they're accessible from pretty much anywhere because they're literally just a network connection away. And so, in principle, they can be leveraged in mobile ways, but clearly they're huge. I think if we look at some of the sort of the details of what this community means by mobilized, one of the points is encode once, use repeatedly. Definitely large language models fit that paradigm, right? We're encoding all of this text and this knowledge that's captured in text in a statistical or neural network model, and we can access that information over and over again in all sorts of creative ways through different kinds of prompting. On the other hand, I think one of the mobilized elements is tracking the evolution of knowledge. And that's where I think there's a much bigger question mark, because these large language models effectively are static models. We can they can produce dynamic outputs, but the once they're pre-trained, and it's kind of, captured in that model. And unless we start then essentially putting version controls around large language models and then doing diffs between them and somehow having mechanisms for understanding how the knowledge that's captured in them has changed, we probably can't do that. So, Mark, I don't know. What is your perspective?
No, I agree with you. And I think what matters is not whether the whether the knowledge is itself mobile or whether the access is mobile. And I think we all agree that there's no difference here. And I think particularly when we think about what's happening on the side of symbolic AI, where people are creating knowledge graphs of billions of triples. Those aren't exactly mobile either, and the goal is to make them accessible from a variety of locations. So I think the mobility issue is just as cloudy in the area of symbolic decision support as it is in the case of LLMs. I think
sure.
When it comes to computation, I don't even want to define computation for our purposes here.
Yeah, I mean, computation can mean lots of different things, right? And I know that we've often, certainly with symbolic AI and kind of traditional knowledge representation, we've been thinking about logic and being able to sort of do deductive closure or transitive closure, just sort of thinking through the logical implications of the knowledge representation. We can't do that kind of computing with these large language models because the knowledge is distributed in the representation, in the mathematical representation. But as you pointed out, at scale, like with these massive knowledge graphs or other kinds of formal knowledge representation, how can we really, in any kind of detailed way, follow through the logical implications of that knowledge? It's very tricky in both cases.
And just to digress for a second, it's interesting. When you think about what led to the advent of symbolic AI in the 1970s, people were really concerned about the transparency of statistical methods for doing decision support. There was a lot of angst about rule-based systems at the time and if they would be sufficiently able to escape brittleness, leading to situations where there's not enough insight into the mechanism by which they operate so that people feel confident in the results of such systems. To look at a large knowledge graph, most people have no clue as to how such a large system is possibly able to reach conclusions. It's the same way that we interact with LLMs and have no idea why it makes the recommendations or it makes the statements that it does. And so in some sense, that whole area of brittleness has come back to us in spades 30 years later, and we don't really have a good handle on it at all.
No, although it's interesting, Mark, because I've observed that even a year ago, before OpenAI kind of blasted onto the scene and changed the whole public perception of what's happening with AI and language modeling in particular, there was a big emphasis on explainability. So, when people were talking about the use of AI in medical decision-making or clinical decision-making, they were very emphatic. No, it needs to be explainable. We cannot possibly have a decision support tool that isn't explainable, that isn't able to provide a context for a particular decision. That I've seen that conversation actually fall by the wayside, because what's happened is the large language models and the generative systems that we have in things like ChatGPT are so convincing linguistically, and the level of competency that's in them, that people believe them without needing an explanation for why it's true, because I think it's expressed in language that they can relate to and ascribe meaning to themselves. And so that kind of need for an explanation is either provided in the response itself or implicit, because kind of the words make sense in that context, and we don't need further justification beyond those words.
That's really fascinating, because again, when you think about the advent of clinical decision support, people were convinced that we needed AI, and in that sense, it means symbolic AI, because physicians would never accept any kind of decision making on the part of computers without the ability for the computer to explain its results. Bayesian approaches, statistical approaches, just were not going to be acceptable because they didn't have that element of explanation. And now, fast forward, and here we are. We have knowledge graphs that are so big, no one can understand what they have in terms of their scope of knowledge encoding. And LLMs, we'll just excuse them for hallucinating now and then without having any ability to really understand whether they're telling us the truth or not. It's like suddenly the sine qua non of intelligent systems is gone.
Yeah, no, that's right. And unless we do kind of rigorous fact checking and propositional truth inference modeling, even on those large symbolic systems, we don't really know for sure that the inferences are valid. And you can control for that to some extent in a symbolic system. We can't control for that in a language model, but we have other strategies for essentially cross-checking the information that's provided by these large language models, which we don't have in the symbolic systems. So it's an interesting world we're in.
Yeah, I just want to recapitulate. We've just said that there's no difference in mobility with respect to current symbolic approaches and language models. We said that they're equally computable. I don't want to argue biological. I think we both would agree that we can put biological knowledge into any kind of formalism like that. Are they knowledge, though? What are LLMs representations of knowledge?
This is the $1 million question, isn't it? So, from my perspective, large language models certainly don't encode semantic relationships, right? So fundamentally, what we're capturing in these models is statistical co-occurrence patterns. Now, very sophisticated ones, and obviously using an incredible amount of context so that we can capture really subtle nuances in those co-occurrences. But it is fundamentally just co-occurrence. And in fact, the tasks that we're training a generative system for is really just a next word prediction task. And so there's no inherent representation of relationships. There's no semantics that's captured there in any explicit way. But what is co-occurrence? Co-occurrence implies that there's some semantic coherence between the words. And the reason words make sense together in a context is because there are connections between them. And so it really starts to raise this question of what is knowledge, right? And, do we need to have kind of formal representation of entities and relationships between them in order to say that there's knowledge? I'm not sure. I personally really believe in the power of semantics. I think one thing that is missing from these large language models is abstraction, thinking at the level of concepts rather than words. You can infer semantic relationships from the information that's encoded in these large language models. So you can work out that cats and dogs are related to each other in some way. Maybe they're connected to the notion of pet, but there's no explicit representation of that. And I think that's one really important difference between what, we as people kind of naturally do and the way we think about knowledge representation and what's in these LLMs. Where that leaves us for deciding whether or not they can contain knowledge, yeah, it's there. It's just implicit.
Well, I kind of grew up with Alan Newell's definition of knowledge, saying that a computational intelligent agent has to have goals, has to have a way of achieving those goals, uses knowledge to bring itself closer to the goals that it believes are the ones that it wants to achieve. I look at an LLM, I don't know what its goals are. And can you have knowledge without goals?
That's a tough question. So really, you're 100% right. Large language models definitely don't have goals. I mean, a generative system, the only goal that it has is to predict the next word in the sequence. At least in the manifestation of ChatGPT. There's probably other ways of realizing that in other kinds of sequence to sequence models. But even in other kinds of sequence to sequence models, we're taking a sequence as input and then producing a sequence of words as output. It's still definitely not capturing semantics or meaning. And is that a goal? I no. I mean, I think it's a very impoverished goal, if it is a goal, and it's certainly not one about problem solving beyond just trying to put the right word one after the other.
Yeah, I mean, I always used to doubt as to whether answering a question is a sufficient goal to call something intelligent, though obviously LLMs do that really well.
Yeah, and I think you're right. I mean, it's certainly not working towards a higher level objective, which I guess, relates to my earlier comment about not having concepts and relationships between concepts, and being able to sort of reason in that more abstract space. They're not working towards goals. They're not meaningful goals, I guess, and they're not really kind of abstracting away from the details of the individual words. I often say to people, we're having a conversation here, Mark. Everybody who's listening to us will not remember exactly what words we said. What they're going to remember is the ideas that we conveyed and the sort of higher level messages. Where's that in a large language model? I don't think it's really there at all.
On the other hand, just abstracting, I think you and I would probably both agree that we could take a large language model, encapsulate it in some metadata that would describe what that model is good for, and make it accessible through some system where it would actually behave in an MCBK kind of way. It might not be the kind of symbolic package of knowledge that we've been talking about in this community for the past few years, but it would certainly be a good representation of knowledge, and it would solve a particular purpose.
Yeah, for sure. And I'm thinking a lot lately about essentially narrow AI, right? Trying to build on the foundations of large language models or other image-based models, foundation models more generally, and then adapting them to specific applications. And what you're referring to there in terms of metadata and trying to capture what these systems are designed for is connected to this idea of adapting them to or applying them to very specific kinds of problems. And I think actually when we're thinking about the use of these models in real world applications, that metadata will become hugely important because it needs to help us define the boundaries of use of the systems. And so we're not just talking about large language models in general, we're talking about large language models that encode knowledge or represent knowledge in some form, and then we apply it for a particular kind of decision or a particular kind of context, and specifying what the expected use cases are for a given application is really important to have trust in it and to understand that we've evaluated it, we tested, we believe it works in this context.
But where I have trouble is I think of a lot of symbolic representations that have gotten a lot of use in this community, but that have validity in various ways, but may not have generalizable intelligence, and obviously do not pass the Turing test. And then I think about large language models, which seem to pass the Turing test without really trying.
Yeah, no, it's really true because there's so much knowledge that's encoded in the large language models, and because they have that amazing linguistic competency. If we take the Turing test kind of at face value, yeah, I agree. They definitely appear to pass the Turing test, and yet I know that these machines are not intelligent, right? I've been trying to remind people that these machines are really simulating intelligence, and they're doing a really great job of simulating intelligence. But are they actually intelligent? No, I don't believe so. And maybe it comes back to that point about goal-oriented behavior and really trying to solve problems. But it just raises another question, which is, okay, if you have a machine that can pass the Turing test, then do we have a better test of intelligence? I don't know. I think we're probably not the ones who are going to solve that problem.
Well, what do you think Turing would think of a large language model?
Oh God, I think honestly he would be impressed, right? Because I mean he was the one who kind of came up with this notion of trying to get machines to encode intelligence, and so I think he would be impressed. Now, whether he would join the camp of people that are in the sort of AI, existential camp of these machines becoming our robot overlords, I don't think so, because I think he would understand that it still is a machine that we control, and maybe it would cause him to rethink his test.
Okay, so if I can summarize what I think we've said, we're saying that we're really no more intelligent than we were 30 years ago. We're still no more explainable than we were 30 years ago. We're still as brittle as we were 30 years ago, and yet we feel we've made a hell of a lot of progress.
Yeah, right. The machines really appear to be much more intelligent. And, to be fair, because of the size and scale of these machines, they have incorporated a vast amount of human knowledge, more than probably any one of us can fit in our, limited neural networks. And so that scale combined with the linguistic competency of the models really, really gives us a knowledge representation that's beyond all possible previous knowledge representations. And that's what I think is really grabbing people's attention. It becomes up to us now to think about, the how we can use them effectively, under what conditions. And then, going back to that metadata and where we started, maybe, we want these things to have some constraints and boundaries associated with them. And that means describing them in computable ways, which then define the ways in which we can use them in other systems or decisions.
Agree completely. This has been fun. Thanks.
Thanks, Mark. Great.